Okay, hello everyone. Okay, so let's get started. Welcome to week six of NPTEL course on Introduction to Astrophysical Fluids. My name is Rohan and I'm a TA for this course, and I'm a PhD scholar at ISC Bangalore. So, before we start with the material for this week, uh, we'll just do a quick recap of what was done in the previous week, that is week five. So, so let's start with a quick recap. So, mm, well, so we studied that for Newtonian fluids, this is how the uh, momentum balance equation will turn out to be, and then from there uh, uh, we studied thin accretion disks, which are basically geometrically thin, and um, and basically which leads us to this assumption del L theta equals to zero, because we assumed symmetry in the azimuthal direction, and v theta much greater than vr, because as they are thin they almost rotate in a Keplerian motion. Vz is also zero because there is no force in the z direction, and similarly del del z is not zero, but the variation of vr and v theta with z, that's we neglect that. So, similarly, like using these assumptions, we wrote the equations for thin accretion disk. So first equation is the equation of continuity, and the second one is this momentum balance equation. So sigma is basically um, integration of rho dz. So it is integrated density over the height of the disk, which is actually small. H by R ratio is small if you remember, because uh, these are geometrically thin disks, so these have very small heights, right? So yeah, so we explicitly derived these two equations in our last week's lecture. So you can go back and look at those if you want to see how these equations come about from the continuity and the momentum balance equation, right? So okay, so then from the okay, so this is, by the way, the theta component of the momentum balance equation. So if you see this momentum balance equation, so you can have three three equations from this, because this is a vector equation. So you can have the r component equation, the theta component equation, and the z component equation. So this was the theta component equation, and if you solve the in the steady state, so by in the steady state you assume that the change in time is zero, so del del t is zero. So if you just put del del t is zero in the continuity equation, so then you will see that r sigma vr will be constant, right? And this is the physical meaning, physical significance of the mass accretion rate m dot, right? So that we saw uh, in the previous lecture. And similarly, if you take the radial component of this equation and do it in steady state, so you similarly get another constant of motion, right? So, and using those two constants, you know, you can find out what should be the viscosity in the disk. So, what is nu sigma? So, nu is the viscosity. Sigma is, as I said, the density, integrated density over the height of the disk. So this is the relation that we got, and we also derived this relation in the previous lecture, that this new sigma is dependent on the mass accretion rate. So higher the mass accretion rate, more is the viscosity in these systems, right? Okay. So yes, mm, now we want to see that, what is the uh, what is the energy or the power that is generated in these accretion disks. So for that, we saw that the power can be estimated from the viscous work done by the viscous force, basically, which is proportional to the viscosity, and also proportional to d omega dr whole square, right? So using that, we calculate the d dt, and that turns out to be of this form. So you see, this has viscosity in it. So we get this term and then some terms, which is d omega dr. So if you remember, the omega for Keplerian motion is proportional to r to the power of minus 3 by 2. So you see d omega dr, square that and multiply it with viscosity, then you get this d dt. And from ddt, if you calculate the luminosity, right? So this is just integration over from r star to infinity, and then integrate over all the shells, and then you get gmm dot by 2 r star. So this is exactly uh, half of the uh, potential energy of the matter that is accreted. So we saw that, you know. All the matter that is getting accreted, uh, half of that energy is being released, and that contributes to the luminosity of the accretion disk, and the remaining half is just contributes to the kinetic energy of the accretion disk. Okay, so now then we stopped the discussion on accretion disk, and we moved on to sound waves and formation of shocks. So we'll continue with formation of shocks in this week's lecture, but we'll see what we have covered in the previous week. So in sound waves, we saw that sound waves are basically nothing but uh, are is the speed at which instabilities or perturbations in the fluid travel from one point to another. Right. So any perturbation that travels from one point to another travels at the speed of sound in that medium, right? So in order to have sound waves, we used a technique which is very useful and is done in throughout in fluid mechanics. So it's called linear instability analysis. So what we did was that we took the continuity equation, and we took the Euler's equation, and we perturbed the system a bit. So for example, what do I mean by perturbation? So for example, we take the density and we just increase the density by a little bit. So, for example, if the mean density was rho naught, we change the density by just a small amount of rho 1, right? So, the new density is rho naught plus rho 1. Okay. Similarly, we did it for pressure. And for velocity, we assumed that the initial base mean velocity was 0, and we added a perturbation, which is v1. So these perturbations are very small, and therefore any higher order terms in these perturbations can be negative. So that's why the name linear stability analysis, because we only consider linear terms in those perturbations. So if put these values of rho, p, and v in these two equations, then and you consider only terms up to linear order, then then you get these two equations from them, right? So this is just del rho 1 del t plus rho naught del dot p 1 time equals 0, and del v1 del t equals to minus grad p1 by rho naught. And this coupled with the equation of state, right? So similarly, if we do the same analysis for the equation of state, this will come out to be this equation, P1 equals to C square rho 1. Now, all these equations, like if you, if you just, take double derivative of the first equation with respect to time and then put the value of dv1 dt from here, and then you will get this equation, right? Now, so use this relation. So you'll be left with this equation, so which is del square rho 1 by del 2t equals to C square grad square rho 1. Now, at this point, we saw that this equation is resembling a wave equation. So very much like what we see in electromagnetic waves or light or something like that, right? So so if you see, from there we estimate that the speed of light, like the whatever the factor is over there, right? So here we see that the speed at which this perturbations rho one and so on move in the medium is at the speed of sound, which is cs, right? Okay. So up to here, we just saw that, what we earlier proposed, that the perturbations in the fluid travel at the speed of light, speed of sound. So now, then what we did was, so basically uh, we took we did a non-linear analysis as well. So this was a linear analysis. So we wondered that what will happen if we include the non-linear terms like second order terms also of the Euler's equation. So this equation will come down to something like this, right? And this is something which is called the inviscid Burgers equation. And uh, and and this is the solution of those equations. So what does it say is that if you start with the wave, which is something like this, which is cos of a cosine wave, right? And as time travels, as it goes along, the wave will will form a shock, right? So basically, you see that this here the gradient du dx is negative. So basically, the velocity of this part will increase, whereas the velocity of this side will decrease. So this solution naturally forms a shock at which you form a very steep gradient of the velocity at some point, right, as the solution evolves. Right? So this is the solution at different times. So we from here we understood that shocks are formed due to nonlinear um, perturbations in the fluid, right? So yeah, so that is one insight that we got from here. So what happens in a shock is that you see a very steep gradient of all the fluid variables, starting from density, velocity, uh, pressure, and so on. Right. So then we studied what are the conditions for a shock, and then we arrived at the Rankine-Hugoniot conditions, okay? In the and that's where we ended. So what do these conditions say? And we will actually use these conditions in today's lecture. So what do these conditions say is that when you have a shock front and before the shock and after the shock, the uh, the 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 density, the mass flux, the energy flux, and the momentum flux are conserved, right? So that comes from the flux conservation equations that we saw in one of the previous lectures, right? So this is the mass flux, this is the momentum flux conservation, and this is the energy conservation uh, before and after the boundary of the shock, right? So U1 is the velocity pre-shock, U2 is the velocity post-shock, and and so on. And you are just a observer who is sitting at the shock boundary or the shock front, and those are the velocities with respect to that observer. Okay. So these are the Rankine-Hugoniot conditions that we saw, and from there we derived what could be the relation of rho 2 versus rho 1, and P2 versus P1, U2 versus U1, and so on uh, in the previous lectures. So from that we can, so given the velocity, density, or pressure before the shock boundary, we can estimate those parameters post the shock boundary. Okay. So yeah, so that's where we ended in the previous week, and now before we start, let me know if you have questions on this part. Okay. So, right. So now, shocks are very widely found in some systems which are called supernova. Right? And so we will study shocks in these systems, but before that, I just want to motivate the physics behind these supernova systems, right? And how do they come about, and what are the types and classes of supernova, and yeah, and and why shocks are so important in these systems. So basically, when a star, you know, uh, uh, reaches this end, right? Uh, for example, right now the sun is burning hydrogen and releasing helium, right? So at some point of time, the hydrogen in the sun will get exhausted, right? And it will be all helium, and then helium will burn, and then carbon, nitrogen, oxygen, silicon, and so on, right? Up till maybe iron. But but many stars, if they're not massive enough, they don't even reach to the iron stage. Before that, the gravitational pull of the star becomes so high that the pressure due to these nuclear reactions cannot balance the gravity, and therefore the star will collapse at some point. And that is how a star reaches its end, and it results in a very huge explosion, and it releases a lot of energy, and that is exactly what is called a supernova. And those are some of the most energetic explosions that we see in the universe, right? So okay, now what are the types of supernova? Okay, so for example, now the thing is, very primarily, supernovas are classified into two types, type 1 and type 2, on the basis of observation of hydrogen lines. So what are hydrogen lines? So you see that, whenever the star burns out the hydrogen in its core, the hydrogen from the core gets exhausted, but there are still some hydrogen left in the outer envelope of the star, right? So whenever the star bursts and it releases this energy, it ionizes this hydrogen, and there could be ionization and recombination, and so for example, and in the ionization and recombination process, what could happen is that an electron could, transition from uh, one shell of the hydrogen atom to a different shell. And this gives to this line emissions, right? And so, for example, well, the emission that comes from the n equals to 3 shell of hydrogen to n equals to 2 shell of hydrogen is called the H alpha line. So these lines basically tell you about the presence of that element, in this case, hydrogen, in the envelope of the star. So so these type 1 supernovas are those stars which have no hydrogen. So because they have lost all the all the hydrogen in their envelope due to winds and those other things. But whereas type 2 supernova are those stars which have hydrogen in their envelope, right? And therefore we see those hydrogen lines in the emission spectrum of these supernova. Now, type 1 are further classified as type 1A, 1B, 1C. on the basis of helium lines, actually. So, for example, type 1A has no helium line but has strong silicon line, whereas type 1B has helium, type 1C has no helium but maybe weak silicon, right? Similarly, type 2 are classified on the basis of, basis of their light curves. So, what are light curves? So, let's look at this image first, and then maybe I'll explain what these are. So, you see, when a star explodes, this releases this huge energy into the envelope, and we see that energy mostly in optical, right? So what happens is that it deposits the energy, and most of the energy are radiated in the very first few days, right? And after that, the energy basically decays, right? So this is the optical luminosity uh, of the star in the y-axis compared to the number of days in the x-axis, right? So yeah, so basically, uh, these classifications of type 2 supernova are on the basis of the properties of the light curves. So, for example, if you see this type 2p supernova, so what happens here is that this light curve has a plateau. So this p stands for plateau. So it means that it releases this energy for a huge duration, and then suddenly it drops, right? So there is a plateau of uh, of energy emitted from this supernova. Similarly, type 2L has this no plateau, right? So you see there is a decrease. I mean, it has a sudden burst of release of energy, and then suddenly it decreases. This is type 2L, right? So type 2B and type 2N. Okay. So type 2N has narrow H alpha emission line. So in other cases, so they have broad H alpha emission lines. What causes this broadening is the fact that since this you know the energy that is released during a supernova is blowing up the matter in the star, so the matter is ejected at very high velocities, and due to these very high velocities, these lines get broadened, which is by a phenomenon called Doppler broadening, right? So if the H alpha lines are narrow, so that means the velocity of the ejecta is low. Whereas if the lines are broad, that means the velocity of the ejectors are uh, very high. Okay. Similarly, type 2B, yeah, so type 2N has narrow emission H alpha emission line. Type 2B has hydrogen in the early days, but only helium in the later phases. And these resemble very much like type 1B and 1C, like this. Okay. So these are very similar to 1B and C, but they have release of hydrogen in the very initial part of their emission. And later they only release helium. They only have helium lights. Okay. So okay. So that is the basic classification of supernova. And just one more point to add to this is that why do we have for example these two broad classes, like what is actually happening in these supernova systems? So for example, why do type 2 has these broad uh, lines, and basically why do they have hydrogen, why do type 1 do not have hydrogen, and why do they have this you know uh, this light curve showing extended emission, whereas in type 1 the light curve falls very quickly. Okay. So the reason is that it has to do with the different structure of the progenitor stars that goes into supernova. So, for example, if there is a star which starts with I mean, a main sequence stars which is not very massive, which is of the less than, let's say, 10 solar mass or even 20 solar mass. So what will happen is that, they won't be able to lose their hydrogen envelope by the time they, explode. Okay. So those stars will retain their hydrogen envelope, and when they explode, mm, they will release this. We will see this H alpha lines from their emission spectrum. Whereas there are other stars which starts with very massive, very high mass, let's say greater than 20 solar mass. So in that case, what will happen by the time they explode, they have lost all their hydrogen envelope with the help of winds and like stellar winds, and therefore they will be only left with this core, which will be carbon, oxygen, or iron, or well, not iron, but carbon, oxygen, silicon mostly. So they will have this type 1 supernova, right? And that's why we don't see any hydrogen lines in this type 1 supernova. Okay. Yes, so that is the basic uh, physics why there are two types of supernova, and why and how are they different. Okay. Any questions? Okay. Okay, so let's move on. Okay, so now we saw that, how the basic phenomenology behind this supernova, right? Now we want to understand, like, why are shocks important in these systems, right? So okay, so before we, you know uh, go into this shock wave, so let's just see a video of animation of how the supernova happens. So this is an animation that is made by me. So for example, this is the star. Let's say that's how we start, right? Let me show you the initial configuration first, and then explain it. So I start my simulation with a star, right? And the star has collapsed. So when it collapses, the core of the star becomes so dense that it collapses onto a neutron star or a black hole, right? Whereas the envelope still remains there, right? And as the in this case, I have considered a black hole. To be formed after the collapse of the star. And as the black hole forms, it accretes the matter from the surrounding of the envelope, that is the remaining of the star, right? So we will see that in action. So for example, so this is just a zoomed in view, and this is the zoomed out view. So this color represents the density of in log scale. And yeah, so basically, if you see, we have a black hole, right? So here, and the star is accreting from the surrounding, and it is throwing out matter. So we saw in the previous lecture that how a black hole accretes, and it can release this jets um, into the envelope, as it explodes, right? So you see that this material, these jets are punching through the envelope of the star, and as it goes out, it creates this shock. Uh, I think you can better see in this image. It creates this shock as the jet punches out through the envelope of the star. Right? So so yeah, so that's why these shocks are very important in these systems, in the supernova type systems, right? So, yeah, we'll see some of the properties, and then we'll try to relate it with how it is important in these system, right? So we'll come back to this. In the meantime, if you see that the shock, this is the wavefront of the shock, right? So if you go back a bit, maybe from here, well. a little bit more maybe. So okay, yeah. So this is you see the shock front, right? So you see the shock front in both the sides, and it is expanding throughout the envelope, right? So this is how shock goes through a medium, right? So we'll see how the shock travels and what are the velocities of the shock and the densities and pressure and so on, right? But this is just a physical motivation of it. Interesting. So So now, as we are seeing that these blast waves are there, and so we assume something called self similarity in this. So, for example, you see this Ri and Rj. So let we assume that these are two radii, two different radii, which are expanding, just as we saw in the previous video that the shock front is actually expanding and it is pushing other matter along with it. So similarly, if we just take randomly two radii, and both are expanding, so this need not be the shock front right now, right? So this could be any two radii and they are expanding, and at the next instant the radii becomes Ri prime and Rj prime. So, so these systems, expand self-similarly, and by self-similarly, I mean the ratio of Ri is to Rj is equal to the ratio of Ri prime is to Rj prime. Okay. Now, now we take one of the uh, uh, one of the radii to be the shock wave, shock front radii, and we denote it as lambda. R by lambda is constant, which we represent as psi r. So r is any radius, and this lambda is the shock front radius. Okay. So now, using a dimensional analysis, we saw that this lambda could only depend on energy, time, and this density, right? So, uh, yeah. So using a dimensional analysis, we saw that this if it depends on energy, time, and the density, so it has to be a relation of ET square by rho one whole to the power 1 by 5. Now this is a dimensional argument, so we don't know that if there is some constant sitting over there. So that's just the constant that which I have denoted as, let's say, n. Okay. But the main thing to see from here is that the lambda depends on time as a power of t to the power of 2 by 5. So lambda is proportional to t to the power 2 by 5. Right? So the shock wave expands with time, so this is the radius of the shock wave, and how the shock wave changes with time uh, as t to the power of 2 by 5. Now, similarly, if you calculate v lambda, which is if you just take a derivative d lambda dt from here, you just take a derivative with respect to time of this expression, so you will get something like this, right? So t to the 2 by 5 derivative is 2 by 5 t to the power of minus 3 by 5. So this is what you get, and this can be expressed as 2n by 5 lambda by t. Okay, so yeah, so from here you can get the velocity of the shock wave front, which depends as lambda by t. Now, okay. So so far so good. Now what we want to do is that we want to apply the RH conditions, the Rankine-Hugoniot conditions that we saw in the previous slide at this shock wave front, right? So as I said that we the way we visualize the shock wave front is that we take it to with respect to an observer who is sitting on this wave front. So basically, that observer is at rest on this shock wave front, and therefore he will see the velocity of the uh, you know the shock coming negative to him. So this is minus v lambda, right? And this is v2 minus v lambda. So this is the the um, the post shock region, right? So so we take U1 to be minus V lambda. So just like we did in the Rankine-Hugoniot conditions, we have the pre-shock and the post-shock region. So your U1 is minus V lambda, and this U2 is basically V2 minus V lambda. Right? So this is it. This is it. Now, if you remember from our previous lectures, so for example, if I just go to the slide, so like here we had derived the rho 2 by rho 1, P2 by P1, and so on, right? So for example, if you take M1 tends to infinity, so that basically means that the shock wave front velocity, the Mach number of the shock wave front is very high. So the shock wave is propagating at very high speeds, very high Mach numbers. So if you see that M1 tends to infinity, this will reduce down to gamma plus 1 divided by gamma minus 1. Similarly, we can get the expression for P2 by P1, right? So P2 by P1 will be 2 gamma M1 square by gamma plus 1. We can neglect this term because this M1 is very high, right? So, yes. So, rho 2 by rho 1 is gamma plus 1 divided by gamma minus 1 as m tends to infinity. And if we look at the first condition of uh, first Rankine conditions, is rho 1 by rho 2 is basically U2 by U1. Rho 2 by rho 1, and therefore this is equal to U1 by U2. And we know this. From there, we can get this expression, and solving this, we get P2 by B lambda equals 2 by gamma plus 1. Okay. And similarly, P2 by P1 is 2 gamma M1 square by gamma plus 1. And from there, we get P2 equals to 2 rho 1 B lambda square by gamma plus 1. Okay. So, yes. Yes, so we get the P2 and the V2 in terms of V lambda, the shock wave velocity. Right? Okay, so now, uh, okay, so before we continue, we want to express these densities, velocities, and pressure like this. Okay, so we'll see why this is a why this this relation will give us a useful expression in the next slide. So but let's assume that we can always represent this density of this region as rho 2 times rho tilde. So where rho 2 is the uh, contains the dimension of density, whereas rho tilde is a dimensionless quantity. So we have done this before, right? So we have expressed this is a dimensionless quantity. Similarly, we can express velocity as v2 times v tilde, and we have this r by lambda factor associated with it. But if you remember that r by lambda is basically a constant, so this doesn't matter. We can always, scale it by a constant. So similarly, P we represent as P2R by lambda whole square P tilde. Again, this is a constant. And we'll see that, if we do it like this, like if we take a single power of R by lambda and double and second power of R by lambda here, it reduces to a better expression. So that's why we do it like this. So we, this is just a change of variables, okay? Nothing else. So similarly, from here, if we just, do take rho, we'll get rho 1 times gamma plus 1 by gamma minus 1 times rho tilde. And similarly, for V, we'll get 4 by 5 P gamma plus 1 R by T V tilde. For P, we'll get 8 rho 1 by 25 gamma plus 1 R by T whole square P tilde. So I'll just derive like how we get to this expressions using this from these expressions. So I just go to my uh, whiteboard and let me derive those. So, okay, so So what did we do is we this is our change of variables v2 v tilde. Well, there is r by t, right? R by lambda. V tilde 2 plus p2 r by lambda whole square tilde. Okay. And yes. And let me just write down these expressions which we obtained from RH conditions. Okay. So these are our assumptions, like the change of variables that we did. And in the second line, we have the conditions that we obtained from the RH equations. Okay. So now what I'm going to do is, so V is equals to 2 by gamma plus 1 B lambda, right? So from here. And sorry, V2. From here, V2 is this. Now, V is V2 R by lambda V tilde. So this will be equal to, this will be equal to 2 by gamma plus 1. And if you remember V lambda from the slide, so V lambda is 2 by 5 lambda by T. We'll just ignore n for now. We'll just take n as 1. So 2 by 5 lambda by T, that is V lambda. That is V lambda times R by lambda. Well, okay, wait. So this is V tilde. So V lambda is there in, this is V tilde. V lambda is there in V2, right? This is 2 by gamma plus 1. So this is V2, right? 2 by gamma plus 1 V lambda. Now we have this multiplied with R by lambda, right? V tilde, right? So this lambda lambda cancels, and we are left with 4 by 5 gamma plus 1 R by T V tilde. I hope that's right. Yes, 4 by 5 gamma plus 1 R by T V tilde. Right. So, yeah. So I guess this expression is pretty trivial. You can just see it from here. Let's do the one for P as well. So, so what is P? So let's see what is P2. So P2 from here is 2 rho 1 V lambda square by gamma plus 1, which is 2 rho 1 by gamma plus 1. And V lambda square would be, well, V lambda, as I said, is, let me write it down somewhere here. V lambda is 2 by 5 lambda by t. So here, and therefore the square of it will be 4 by 25 lambda square by t square. So you see that, here lambda lambda cancels, and that's why we took a single power of r by lambda. So here you will see that, the lambda square, the r by lambda square will cancel with this lambda square. And that's why we took a second power of r by lambda to make the expression simpler. Okay. So this is P2. Now, what is P? P is P2 r by lambda whole square P tilde. Right? And so we just multiply this P2 with r by lambda square. So this lambda square will cancel. And this is 4 times 2, 8 rho 1. And this is 25 gamma plus 1. Lambda square will cancel. So we're left with r by t whole square P tilde. Right. So this is the expression. And that is what we have open here. 8 rho 1 by 25 gamma plus 1 r by t whole square P tilde. Yeah. So yes, so now we will see how we can use these uh, variables to find the properties of shock waves, and we'll see how these variables vary uh, across these shocks. And as we earlier said, that r equals to lambda is the radius of the shock, and at that radius, this uh, you know at r equals to lambda, psi would be psi lambda, right? And these will be all 1 because this rho is equal to rho 2, right? V equals to V2 at the shock boundary, right? So that was what we started with in the Rankine-Hugoniot conditions. Okay, so right. So what are we trying to do here is that the Euler's equation and the continuity equation and try density, the pressure, and the velocity varies across the shock boundary, right? And that's why we, expressed these, just the density, velocity, and pressure like this. So now we will use these variables and try to see uh, what are the solution of these variables and how they vary across the shock boundary. So as I said, xi equals to 1 is the shock boundary because xi is r by lambda, lambda is the shock radius. So at the shock radius, r equals to lambda, so xi is 1. Right? Now just recall the uh, uh, continuity equation and the Euler's equation. Right? And the continuity equation, as we saw, can be written like this in spherical coordinates. Similarly, the Euler's equation can be written like this in spherical coordinates. Right? So, and we also need the uh, equation of state, right? So here we consider an adiabatic equation of state. So adiabatic equation of state says that p rho to the power of minus gamma is constant. And so here, if you see that this just says the same thing. So this is ddt, right? So as we saw uh, in the probably week 1 or 2, that ddt is del del t plus v dot del. So this is ddt of p to the p rho to the power minus gamma ln of that. So that just says that ddt of something 0. That means this is constant. So that is p rho to the power minus gamma is constant, which is equivalent to the adiabatic condition. Okay. So, right. So from here, uh, right. So we have three equations and three variables, rho, v, and t. Okay. So now we are trying to solve these three equations and three variables and try to see how they vary in the shock region. So again, we do one change of variables in this equation. So instead of r and t, we want to have this variable psi. So such that we have this differential equations not in terms of r and t, but in terms of a single variable psi. Right? So we'll have three differential equations in which the dependent variable is only one, that is psi, instead of two. So how we do that is, we express del t as minus 2 by 5 xi r by t d xi r, and del r as xi r by r d xi r. So we'll derive this again. We'll go back to the whiteboard and we'll see how this comes about. So, but you have to remember that the original definition that, r by lambda is psi, and this is how lambda varies as t to the power 2 by 5, and so uh, this two relation. So let's see how we go about this. Okay. So as I said, r by lambda is psi r, right? And lambda is proportional to t to the power of 2 by 5. So k is just the proportionality constant. So so if we just take del f del t, so we can use chain rule and write the derivative in terms of psi. So this will be del f del psi and times del psi del t. Right. Right. Now, mm, now let's find out what del psi del t is. So del psi del t is equals to del t of r by lambda. Okay, so okay, let me just repeat this part. So we know that r by lambda is equals to psi r, and lambda is k t to the power of 2 by 5. So lambda is proportional to t to the power of 2 by 5, and k is just the proportionality constant that I considered. So therefore, we can write del f del t as equals to del f del xi times del xi del t, which is just the chain rule. Right. Now we just want to expand del xi del t. So this is del t of r by lambda, and this can be written as minus r by lambda square times del lambda del T, right? And that is minus r by lambda square. Del lambda del T is 2 by 5 k t to the power of minus 3 by 5, right? So we just take the value of lambda from here, take the derivative, and we get this. Okay. So this if you remember, this is v lambda, and this is 2 by 5 lambda by t. Okay. So this is minus r by lambda square times 2 by 5 lambda by t, and therefore, okay, it is not coming. Okay. Let's see. So yeah, so this is minus r by lambda square times 2 by 5 lambda by t. And this will be equal to minus 2 by 5 r by lambda times 1 by t. Okay, so just cancelling one lambda, and then if you remember, r by lambda is psi r basically. So minus 2 by 5 psi r by t. So now what we can do is that we can write this equation as minus 2 by 5 psi r by t del f del psi r. Right? So that's why we can write del t is equals to minus 2 by 5 psi r by t del psi r. Okay. So yes, so this is just from simple chain rule differentiation arguments. We just showed that del t could be represented in terms of psi r, del psi r. Similarly, let's do this for del r. So again, del f del r can be written as del f del psi r times del psi r del r. Okay. Now let's expand del psi r del r. That will be equals to del r of r by lambda. So del r of r by lambda is just 1 by lambda. And 1 by lambda, if you see from here, this equation is just psi r by r, right? So yes, this one can be written as psi r by r times del f del psi r. Okay, so therefore del r is equivalent to psi r by r del psi r. Okay. So these are the two relations of del t and del r with del psi r. Okay. Now let's go back to the slide. So yeah, so del r is ir by r, dt is ir that we obtain, and this is like this. So from two variables r and t, we obtained this differential equations in terms of one variable, which is psi r, right? And psi r is basically r by lambda. Okay. So now if you know, replace del t with this thing and del r with this in these three equations, right? So we'll obtain these three equations. So this is the first equation, second, and This is the third, right? So you just have to substitute del del T with this thing here, del del R with this thing here. Okay. So I'll just show how we can do this for one of the equations. So let's say the continuity equations, but you can do the same for the other equations and obtain this equation. So let's do it for the continuity equation. So first, so, okay, so let me start from here. So what is del del T and del del R? So these are the things, right? And if you remember from our uh, previous slide that we had expressed rho like this, we have expressed V like this, and we have expressed P like this. We had derived these expressions earlier. Now, what was the continuity equation? The continuity equation was del rho del T plus 1 by R square del del R of R square rho VR equals to 0. So we are gonna do two things. In place of del del T, we'll substitute this. In place of del del R, we'll substitute this. In place of rho, we'll substitute this. In place of V, we'll substitute this. This equation will not have any pressure. So if we do that, so let's see. Del del T, let's look at the first term. Del rho del T, that is minus 2 by 5 psi r by T, and then del del psi r of rho, right? So rho I have written as gamma plus 1 by gamma minus 1 del rho prime rho tilde psi r, right? So I substitute rho from here, and the second term is 1 by r square. Uh, okay, let's keep del del r for now. I'll later substitute with this, but right now let's substitute rho with this and v with this, and let's see what happens. So del del r of r square rho tilde v tilde r. So this r is uh, coming from this v. So I just substitute v with v tilde r. So there are some other factors which I am gonna write down. 4 rho 1. So this 4, this rho 1 And then there is gamma plus 1 by, so gamma plus 1 gets cancelled. So this gamma plus 1 and this gamma plus 1 will get cancelled. So for rho 1 divided by 5 gamma minus 1, and there is also a t. So this gamma plus 1 cancels. So 4 by 5 gamma minus 1, rho 1, and then there is 1 by t. So this r is being taken inside this. Okay, so that is equal to 0. Now from here you can see that we can take rho 1 common and it will get cancelled from both the terms, right? Similarly, we can take t common, it will again cancel. Similarly, gamma minus 1 will also cancel, right? So what else? Yeah, 5, this factor of 5 will also get cancelled. So after cancelling those things, the first term becomes minus xi r del rho prime del xi r, and there is minus, yeah, there is 2 gamma plus 1 factor times 2 gamma plus 1, right? The second term becomes, so you see this is r cube inside, right? So I'll just, what I'll do is that I'll use the chain rule, right? So let me write this one like this. So this is del r of r cube rho tilde v tilde, right? So this, if I expand, so this will be 3r square rho tilde v tilde plus r cube del r of rho tilde v tilde, right? Okay, so that's what I'm gonna do. And if I do that, so the r square of this term will get cancelled with the r square here. So this will be 3 rho tilde v tilde plus second term contains r cube by r square. So that will be r times, well, r times del r of rho tilde v tilde, right? That is equal to 0. Yes. Yeah, I guess that's right. Okay, now the last step to do is replace this del r, right? So we'll replace this del r with xi r by r del xi r. So the first term will remain as is. We'll just take this 2 gamma plus 1 factor. We'll divide the whole thing with 2 gamma plus 1. So therefore, we'll get 1 by 2 gamma plus 1, and within bracket we'll have 3 rho tilde v tilde plus this r times del r of, uh, so del r is xi r by r del psi r rho tilde v tilde equals to 0. So this r will cancel again over here. So this is just psi r del psi of del psi r of rho tilde v tilde, right? So this is equal to 0. This is the final equation. Okay? So also if you see from here, so this is what we get. Xi r del rho tilde del xi plus 2 by gamma plus 1, 3 rho tilde v tilde plus xi r dt xi r of rho tilde v tilde equals to 0. So that's what exactly what we got from the continuity equation. Similarly, if you put these values and put the values of rho, v, and p, you will get this equation from the Euler's equation, and similarly, we'll get this equation from this equation of state. Okay. Now, okay, so we have derived these equations. Now, so these are three differential equations, and we have three initial conditions, right? So these are the initial conditions at r equals to lambda. Um, so basically at xi equals to 1, the rho p and p is equals to 1. Right? So you have three first order differential equations, three initial or boundary conditions, and you can just solve these equations, right? So you can solve them numerically or um, yeah. So you can solve them numerically using a computer, and this is what the solution you will get, right? On the top right corner is the solution that you get after you solve this. So yeah, a couple of things to see is that, so this is from xi equals to 0 to 1. So this is the xi equals to 1 is where the shock front is. So this is inside the shock front, and yeah, and if you see that, at the shock front, the initial the boundary conditions of this differential equation says that all of these terms will go to 1, right? So v equals to v1, rho equals to rho1, and p equals to p1. But you see that apart from velocity, so this density and pressure has a very sharp increase close to the shock boundary. Okay. So, for example, like, if you look at the density, right? So there is very low density, very much inside the shock boundary, but very close to the shock boundary, the density rises up very rapidly. So there is a very high density of material before the boundary of the shock, right? Similarly, the pressure before the boundary of the shock rises up exponentially, like very high. Well, then the velocity, increases gradually, right? And similarly, you can also calculate the temperature, you know, and the temperature at the shock goes to 0. So temperature you can calculate just by P by rho. So yeah, so the temperature at the shock goes to 0. So these are the solutions of these three equations, right? So now if you go back to the video that I was showing for uh, you know this core collapse model and how the shock gets released. So if you see from here, so if you see at the shock boundary, as I showed you that, this blast wave propagate. So let's uh, go back a while. So you see the shock boundary, so and you see the density color from here. So at the boundary of the shock, you see this yellow, shade, whereas inside you have this blue shade. So that means that the density, rises. It has a very high density at just the, blast wave front, right? So whereas inside the blast wave front, the density is very low, which is shown in the blue over here. Whereas uh, at the shock wave front or very close to the blast wave, the density is in yellow, which shows a very high density compared to the inside part. So that's also what we see from these simulations as well. Okay. And if play the simulation for a long while, you will see something, the star, this shock wave, blasting the star and destroying it, and ultimately, pierces through the envelope and going out uh, into the interstellar medium, which we then see as gamma ray bursts or GRBs, right? And these GRVs are one of the most powerful, energetic radio sources in the universe, right? So you see that how the formation of the black hole at the center or the neutron star at the center could, break apart the star. So you see the how the star has broken apart and releases this high energy that we see from the supernova, and which are also sometimes associated with this gamma ray burst as well. So these are only observed after this shock wave or the jet you know escapes from the envelope of the star. Right? So yeah, so this is just a zoomed in view, and this is a zoomed out view, and yeah, so that's how it goes. So yeah, so let me just play the video once again from the start, and yeah, and we'll just take a break as this video plays. Okay? So we'll be back in 5 minutes. Okay? All right. So, yeah. So, like as you see that, as the shock wave breaks apart the star and it escapes from the envelope, uh, the star breaks apart. The envelope of the star breaks apart, and uh, you know, so the central engine, so the black hole at the center of the neutron star, it dies because it doesn't receive any more supply of matter, and therefore, the supernova, the energy or the optical luminosity of the supernova dies down after that. So you saw the supernova light curves, right? So the I mean, after a certain time or a few days, the light curves, goes down, the luminosity, falls, and and this is the reason that why the luminosity falls after a few days. Okay, so well, these timescales are not of the order of few days, obviously, but if you evolve this system for long enough, that's what you expect to see. All right, so right, so that's all for supernova, and now let's move on to something else. So So these extragalactic jets, right? So we talked about these jets from accretion disks, and even in the supernova systems, we saw these jets moving out from this accreting systems. So jets are very closely associated with um, any kind of accreting system. And people have proposed many models for these jets. So one of the popular model that is still people follow are Blandford-Snike and Blandford-Payne mechanism for releasing these jets from accreting systems. So we'll not talk about those systems, but definitely you can look at their papers uh, and uh, and see how what are those mechanisms that produces these jets. So here we'll talk about the Blandford and Rees model, uh, or the Laval Nozzle Model, which produces extragalactic jets from these accreting systems, from any accreting systems. So we will see how we can, what is the mechanism that these jets can be produced. So, for example, we consider a steady adiabatic gas. So, as we know, the steady state means the time derivative is zero. There is no variation with time, and adiabatic is P equals to K over to gamma. And if we just do dp dx, we'll get gamma P by rho d rho dx. Okay, so this is just taking derivative of this equation. And gamma p by rho is cs square, as we know. So cs square dx. And now we write down the continuity equation. So this is del dot rho v equals to 0. So if you write down the continuity equation and if you write it down in the integral form, so if you just do integration of del dot rho v over some volume dv, and using the divergence theorem, you can say that rho v dot ds integration is equals to 0. So from there, you can say that rho v times the area, the ds is the area, equals to 0, right? So rho v area is a constant term. So that's what we get just from the continuity equation. And if you just take the derivative of that rho v a equals to constant, and if you take derivative on both sides with respect to x, you are left with this equation, right? So 1 by rho d rho dx, 1 by dt dx plus 1 by a dA dx equals to 0, right? Now, another thing is that, we also write down, so this is the continuity equation. Now we write down the Euler's equation. And the Euler's equation we only consider, so del t is already 0, so v dv dx, so v dot del v term. And on the right side, we have del p by rho term, right? So this is minus 1 by rho dp dx. And we already saw that dp dx is c squared d rho dx. So this is minus c squared by rho d rho dx, And from here, we can, so basically from these two equations, so this equation and this equation, we arrive at this equation, right? So, so what you do is that you just, you know, you just replace this d rho dx with minus 1 by v dv dx minus 1 by a dA dx, right? So you replace this d rho dx with this term, and you are, you know, you obtain this equation. So this is m, which is Mach number v square by c square, and 1 by v dv dx equals to minus 1 by a dA dx, right? Okay, so we don't have to, solve this equation explicitly, but we can get some idea about what this equation says without even solving it, right? So for example, uh, um, let's consider dVdA, right? So for example, before going into there, let's see one thing. Okay, so V is positive, right? So let's consider as flow in one direction. So for example, like the velocity of the fluid is dominantly in a single direction, and then V is positive, right? Let's consider V positive, and A is also positive. So dx is, dx could be positive or negative, but A is positive, V is positive, and so what does it say that, when m is less than 1, so if m is less than 1, so this term is positive. Okay. So if this term is positive, so that means dv dx and dA dx has to be of opposite signs, right? So if this is positive, so then dv dx and dA dx, uh, I mean, one of them has to be negative. Okay. So if we calculate dVdA, which is dVdx by dA dx, as both of them are of opposite signs, so this has to be less than 0 for m less than 1. Whereas for m greater than 1, the opposite thing will happen. So m greater than 1 means this is negative. So this negative and this negative sign will cancel. So dVdx and dA dx will be of same sign. So dVdA is dVdx by dA dx, and that will be greater than 0 for Mach number greater than 1. Right? For Mach number equals to 1, if you see, if you put m equals to 1 here, so then dA dx will be equals to 0. Okay. So yeah, so this is what we can understand from this equation without explicitly solving it, but we want to see how it helps, how it helps us, right? So, for example, let's say in case of jets or winds, or we saw that so basically what we are trying to do is we're trying to design a system such that gas is flowing or a fluid is flowing through that system, and initially it was at subsonic speeds, so that means initially it has Mach number less than 1, and then it went into a supersonic speed. So Mach number has less than greater than 1 after that. So basically, what you have to do for Mach number uh, less than 1 is that your uh, dA, right? So your dA should be negative, right? So as given here. So whereas for so once it has to go from less subsonic to supersonic, it should be should be equal to the speed of sound. So that means Mach number should be equal to 1 at some point, right? So at that point, dA dx should be 0. So that means the area do not change with x. So it has to go through a constant area, surface as it goes from subsonic to supersonic. So this is the constant area surface where the where it achieves sonic speed. Okay, so this is the throat of this D-level nozzle. Okay, right. So now in the Mach number less than 1 region, we saw that dVdA should be negative, right? So so V is always positive in this direction, right? But dA has to be negative. So dA negative means the area decreasing with with x, or in this x direction. So velocity is always in this direction, and from left to right, right? So v is always in the positive direction, and therefore dA has to be negative. So that means the D-level nozzle in the subsonic region should have a decreasing area with respect to x. Similarly, it will have a constant area with respect to x in the throat region where it achieves sonic speed. Similarly, for m greater than 1, dVdA should be positive. So that means, it you know, the dA should also be positive. So that means, the dA, the area should increase with x in the supersonic region as well. Okay. So in the subsonic region, dA negative, because we are accelerating the fluid. So because dV is positive always, and in the throat region, uh, uh, dA is 0, right? And in the supersonic region, dA is greater than 0, as dV is always positive, because we are always uh, accelerating the fluid, right? So this was the D-level nozzle mechanism for launching these supersonic jets, which gets emitted from these accreting systems, right? So Blandford and Rees use this mechanism to explain why we see this extragalactic jets in almost coming from almost all galaxies, right? So as we know that all galaxies have a active galactic nuclei or a supermassive black hole at the center, right? And most of them are accreting and hence are active. And therefore, whenever that black hole is accreting, that black hole releases this jets, right? And these jets are passes through this galactic gas, and and it then finally gets ejected into the extragalactic medium, right? So this is what we see as extragalactic jets from almost every galaxies, right? So Blandford and Rees proposed their model that so whenever we have a supermassive black hole at the center, so they passes uh, through this structure which is similar to this D-level nozzle, right? And so they have, so you see there are a lot of gases and fluids in the galaxies, right? So they create this throat of this D-level nozzle, right? So where this jet achieves the uh, sonic speed, right? And then finally, as it goes out in the extragalactic region, so this you see that this uh, this uh, this jet gets a huge room for expansion, right? And this room is what is causing this dA greater than 0 region, and there the jets get supersonic speeds. They achieve supersonic speeds, and finally they get released from the extragalactic medium, which we finally observe in radio. Okay? So that is the mechanism for launching this extragalactic jets. Okay. So, but as I was saying, this Blandford and Rees model, has been modified, and this same person, Roger Blandford, later published two papers along with Payne and Znai, and there they propose that this D-level nozzle is not sufficient to uh, produce this huge powerful jets into the extragalactic medium. So we also need magnetic fields, and which are very important in uh, producing this powerful jets, right? So yeah, we are not going to study those Blandford and Zach mechanism, but it's good to know that those are the two mechanisms that are still being followed for as one of the primary mechanisms for launching these jets. Right. Right. So okay, we move on. Okay. So now we have reached the last part of our of today's lecture. So instability. So in the previous week we did some uh, we did a little bit of analysis of we did a little bit of linear stability analysis when we saw perturbations in the fluid, right? So now, so basically what you do is you perturb the fluid or you change the density, velocity, and the pressure by a small amount. And that's how you perturb the fluid, and you just see that how these perturbations, travel inside the fluid. But now I mean, what decides whether those perturbations would be stable or unstable, right? So, for example, let's say you perturb some system and that system comes back to its initial state, right? Again, after some time, by some oscillations or, doing something. Then you can say that, okay, that is a, you know, stable perturbation or the system has regained its stability, right? So, for example, if you have a spring mass system. So if you just pull the mass of the spring and let it oscillate for a bit, and then again due to the drag force or the viscous force, the system again regains back to its original position. So that is a stable position, right? So that's a stable perturbation. Whereas if uh, perturb the system by too much, right, by a very huge amount, such that the system do not comes back to its original position, and it follows some it goes to some other state, right? So then we say that the system has become unstable and it leads to turbulence and all those things. Okay, so yeah, so this is what we did the linear stability analysis in the previous week, but now we are going to see a particular type of instability, which we call the Schwarzschild instability. Okay, and we'll see how what gives rise to this instability. Okay. So we consider basically an adiabatic fluid. Okay, so for adiabatic fluid, you know that P by rho to the power gamma is constant, right? And so what we do is basically this is expressed in this picture, right? So for example, so if you have a fluid, right, and in a fluid, you know that the fluid has some temperature, density, and pressure, right? And as we know that the pressure and temperature of a fluid is basically uh, dpdz and dtdz is negative, like if z is in the upward direction. So in this direction. So as we go down in the fluid, the pressure will be pressure and temperature both will be higher in the bottom of the fluid. Right? So let's say we consider one layer of the fluid which has some density and pressure rho one and p1, and another density, another somewhat higher at some higher position. It has some density and pressure rho two p2. Now we take some bubble of within that fluid which has some density rho 1 star, p1 star, and we displace the bubble. So this has some density and pressure different from the surrounding. Okay, so that's why this bubble is formed. Now, if we displace this bubble to some higher position, which has surrounding density rho 2 and pressure P2, and we displace this bubble adiabatically, such that this condition holds P by rho to the gamma is constant from here to here, right? So it displaces this bubble adiabatically. And now we want to see that whether if we displace this bubble, whether it would be stable or unstable. So what we want to what did we say that about stability is that if it comes back to its original position, it's stable. If not, it's unstable. So what will make it come back to its original position is that this condition, the rho 2 star and rho 2, right? So if rho 2 star is less than rho 2, like some if this bubble has even lower density compared to the surrounding, it will you know keep on going up, right? So therefore it will be unstable. Whereas if rho 2 star is greater than rho 2, so if the density becomes higher of this bubble than the surrounding, then the bubble will sink again and come back to its original position. And therefore this uh, this system will become stable. This perturbation of the system will be stable, right? So this is just the basic idea, right? Now we want to see that I mean, what is the condition that leads to this and or this. So as I said, that we are displacing the bubble from this 1 point to 2 point adiabatically, and therefore this relation will hold. Now, what we do is that we check that P dash P prime equals to P plus dPdz delta C. Okay. So therefore P prime by P equals to 1 plus 1 by P dPdz delta Z. So there is a little bit difference in notation over here. So actually P is the so let's take rho P at the is the density and the pressure at this point, and rho prime P prime as the density of the uh, density and pressure at point 2, right? And these are the density of the surroundings, whereas the density of the bubble is rho star and P star at this point, and we'll see the density at this point. Okay. So P prime equals to this. So this is just a simple Taylor series expansion, P plus dPdz delta Z, and just dividing both sides by P, this we get this. Similarly, not similarly, using this relation, rho star by rho equals to P dash by P, we get uh, this this relation, right? So this is just this thing whole to the power of 1 by gamma. Right. Now, we get this, and similarly we can uh, you know uh, we can just take this to this side and consider this terms as a small term. So by just doing again binomial expansion, we get this thing. So rho star equals to rho plus rho by gamma p dpdz delta z. On the other hand, we can also get rho prime, which is the surrounding density in this region, uh, as uh, well. Okay, so rho star is basically the density of the bubble at this height, and we considered that the density of the bubble at this height was similar to the density of the surroundings, so that is rho. Okay, so yeah, that should be mentioned, right? So we get rho stars, which is the density of the bubble by automatically moving it to the position 2, and rho prime, the density of the surrounding at this position, is given by simple again a Taylor series expansion of rho plus d rho dz delta c. Now, from we also have the relation of ideal gas, which is P equals to rho RT by M, and then again taking the derivative on both sides, we get d rho dz equals to rho by P dP dz minus rho by T dt dz. Okay, so that is just by taking derivative of this equation. Okay, so now we have rho star, we have rho prime, we just do rho star minus rho prime. So this will cancel, we'll get so again, you can express this d rho dz in terms of this in this equation. So sorry, in this equation, just replace d rho dz with this and just do rho star minus rho prime. You will end up with this equation, which is minus 1 by minus 1 minus 1 by gamma rho by p dpdz plus rho by t dtdz. Okay, so this is rho star minus rho prime. Now, if you remember what we said for the condition for unstable equilibrium is that this rho star has to be less than rho prime. So this has to be negative for it to be unstable. Whereas if it's greater than 0, if it's positive, so that means that it will be stable, right? So now let's have a look at the criteria for stability. So as I said, for stability, this has to be greater than 0. Now, as we know, for a fluid, pressure and temperature, all is negative with Z. So dpdz and dtdz is negative. So we can just say that if this is greater than 0, so that means this is greater than 0. And if both are negative, so we can take mod value of this and we can arrive at this condition. So this is the criteria such that this perturbation will be stable, and this is called the Schwarzschild stability criteria. Okay. Okay. So yeah, so as far as Schwarzschild stability criteria goes, so this is it. So this just means that if this condition is satisfied, this bubble will go back to this position, initial position. But if this condition is not satisfied. In other words, this 1 by t dt dz is greater than this term. So that means that this, bubble will keep on rising, and therefore the system will be unstable. Okay. So now we want to see another thing that if this system is stable, so you displace this bubble from here to here. So what if the system is stable? This bubble will sink down, right? Now, if it sinks down, what will happen? Like just like a spring system, right? If pull the mass, it will it will go to the side, and then if you release it, it will oscillate about the mean position, right? Oscillate about the position zero. So therefore, if you displace this bubble over here, what it will do? It will go up and then sink down, and then it will oscillate about this point, about the initial point, right? So similarly, so that will happen only if the system is in stable condition, like this criteria is satisfied. If this criteria is not satisfied, then this will keep on rising forever, right? Now we want to see that how will it oscillate, like what will be the frequency of these oscillations, right? So if we displace this, if we make this perturbation, what will be the frequency of this oscillations? Or if if the system is unstable, what will be the time scale at which it will keep on rising? What will be the uh, you know what will be the rate at which this bubble will move forward, move up? So in order to do that, we just do a simple, buoyancy force calculation. So for example, this term rho star minus rho dash is basically the mass displaced, right? So rho star minus rho prime times g is the mass of fluid that is displaced. And that is equals to the force. So that's equals to the buoyancy force. And this is just the Newton's law. So rho times acceleration, ma term, is equal to the buoyancy force, right? So using this equation and just replacing, putting the value of rho star minus rho prime from here, we get this equation, right? So now if you see, so this is just a equation for an harmonic oscillator, right? So just as we're saying that, there's an equation like if you displace this mass spring system and displace this fluid system, these are equivalent. And those that will also oscillate and this will also oscillate, right? Now, just a brief, aside about how this oscillation behaves. So just remember the form of this equation. So if you see, so this is d2 del z dt square plus some constant times delta z equals to 0. And if we consider this constant to be n square, right? So this constant is n square. And this is called the Brunt-Weisel frequency. Now, what is the physical significance of this that we are going to see uh, just here? So let me go to whiteboard. Okay. Okay, so you see that we have this equation of the form del 2 del z del t square plus n square, which is the Brunt-Weisel frequency, n square del z equals to 0, right? So now you see that, uh, you know, let me write down the expression for n del n square as well over here, 2 by t. Sure. Yes. So, okay. So this is the expression for um, n square. Now we saw the Schwarzschild criteria, right? So the Schwarzschild criteria was this dTdz should be less than this. So this is stability criteria. Now what happens if dTdz is greater than this, and what happens if dTdz is less than this? So you see the if dt dz is greater than this part, so that means the Schwarzschild criteria is not satisfied. So that means the system becomes unstable. Okay. So this is unstable. Whereas dt dz less than this, system is stable. Okay. Now let's consider this stable system at first. So dt dz less than this. So if dt dz is less than this, so that means this is greater, so this is negative, right? So this whole term will become negative. So n square is negative. So do you know like what is the solution for this system with n square negative? Okay. So the solution will be delta z equals to a e to the power of I kt, right? Or basically nt. So this is the oscillation frequency, right? At which this oscillates. So you can write this as a cos of nt plus uh, d sine of nt, right? So this is the oscillation frequency at which this oscillates. So this happens when the system is stable, right? On the other hand, if the system is unstable, then dt dz is greater than this, and if this is greater than this, so then it just says that this n square is basically positive, right? So if n square is positive, so that means that the solution would be delta z equals to a into the power of minus nt, right? So that just means that the perturbation will grow as with this factor of n, right? So that is what is the significance of this Brundtweissela frequency, this n, right? So if the system is unstable, this will grow as n, the perturbation will grow as n, the instability will grow as n, and if the system is stable, it will oscillate, and the oscillation frequency is given by the Brundtweissela frequency, right? So that is the physical significance of this Brundtweissela frequency. It's given as n. Okay. So yeah, so that is it for this week, and this is these are the references, and especially for instabilities and all, this Atchison book is good. You can see the third chapter, if I remember correctly. It is on waves, and this is for accretion. If you want to look at it, this also contains good description about the shocks and those things. And similarly, this book is on some basic fluid mechanics. So yeah, so that is it for this week. Let me know if you have any questions. Okay, if you don't have any questions, we can then close the session. We'll again meet next week, Tuesday, same time. Okay, see you.